Deploying robust, autonomous AI agents local first on single-node hardware without cloud dependencies presents a strict engineering constraint. To analyze how to maximize performance under these conditions, we are looking at a specific hardware baseline, the NVIDIA DGX Spark, utilizing the GB10 Grace-Blackwell Superchip equipped with 128 GB of unified memory. Despite the high-end specifications, there is a contradiction in the developer community. Engineers deploying 120 billion parameter models on this exact hardware are reporting sluggish execution speeds, specifically noting a sleep-inducing 16 tokens per second. Yet, independent testing validates two highly optimized states on the exact same machine: a stable 24 tokens per second for a 120 billion parameter model, and over 218 tokens per second for a 35 billion parameter model. Maximizing single-node performance is not achieved by chasing raw parameter count. It requires meticulously aligning memory limits, serving engines, and native quantization kernels. Solving this hardware-software alignment is the only way to achieve truly sovereign, enterprise-grade autonomous workflows that operate efficiently in isolation. The primary architectural constraint is fitting the 120 billion parameter Nemotron model into a 128 GB unified memory architecture, where the CPU and GPU share a single memory pool. Using NVFP4 compression, the storage requirement for the model weights is exactly 75 GB. The standard NVIDIA NIM deployment container critically fails in this environment. The wrapper contains a hard-coded safety guard that forcibly clamps GPU memory utilization to 50%, or roughly 60.8 GB. Because the 75 GB weights cannot fit, the container creates a synthetic out-of-memory error and dies. Bypassing the NIM container and deploying the raw vLLM OpenAI nightly image acts as a manual override. This allows the architect to push the utilization boundary to the 75% mark, securing 96 GB of reserved space, and load the weights. Within that 96 GB reservation, the model weights leave a remaining budget of 21 GB specifically for the KV cache. This leaves 26 GB of system headroom outside the vLLM reservation, which is required for the OS and background networking. If the context window is pushed too high, the KV cache footprint expands beyond its budget and overflows into the system headroom, filling the memory pool completely. This forces the OS to aggressively swap tensors to the local NVMe SSD. The resulting PCIe bandwidth choke starves the GPU and crashes the system. Stabilizing the node requires a kernel-level fix, permanently disabling OS swap to prevent this PCIe thrashing. Overriding container limits and enforcing strict memory boundaries transforms guaranteed crashes into baseline operational stability. Once stabilized, the 120 billion parameter model on the vLLM stack achieves a steady state of 24.1 tokens per second. This setup is highly stable, maintaining its throughput across a massive context window, validated up to the hardware limit of roughly 130,000 tokens. This 24-token ceiling causes confusion in the community, as developers expect the NVFP4 format to run much faster on Blackwell hardware. The architectural reality of this vLLM stack is that NVFP4 is functioning solely as memory compression to fit the model into the shared pool. It is not functioning as a compute accelerator. Because this specific software stack lacks native FP4 compute support, the system engages the Marlin kernel as a fallback. The Marlin kernel must manually dequantize the NVFP4 weights back to BF16 in real time before math can be executed. This constant dequantization creates an unbreakable throughput ceiling, regardless of how much memory is available. Treating storage quantization formats as compute accelerators leads to false architectural expectations and unoptimized deployment strategies. To reach higher speeds, we must pivot the architecture. We replace the 120 billion parameter vLLM stack with Qwen 3.6, a 35 billion parameter model running on the Atlas engine. The first major optimization of the Atlas engine is its use of native Rust and CUDA NVFP4 kernels. This removes the Marlin dequantization penalty entirely, allowing for direct hardware acceleration. The second optimization is the activation of multi-token prediction, or MTP, speculative decoding. Operating at k equals 2 drafts, the engine predicts and verifies multiple tokens in a single forward pass without the overhead of a separate draft model. The compounding result of native kernels and MTP is a 9-time speed multiplier, leaping from 24 tokens per second to 218. Matching the software engine to the hardware's native quantization capabilities shifts the throughput ceiling of the entire machine. This presents a trade-off. Does shrinking the model from 120 billion parameters to 35 billion parameters destroy its ability to function as a reliable agent? On the tool eval benchmark, the massive 120 billion parameter Nemotron model achieves a score of 93 out of 100, though it scores only 67% in parameter precision. While the overall score is excellent, the model struggled slightly with strict formatting during complex tool calls. The 35 billion parameter Atlas architecture, by contrast, is flawless. It achieves a perfect 100 out of 100, handling unit conversions and multi-step chains without error. It maintains high responsiveness with a median turn time of 0.8 seconds, compared to 6.6 seconds for the larger model. However, there is a hidden cost. The speculative decoding stack is more memory-hungry, leading to performance cliffs at maximum concurrency that the 120 billion parameter model avoids. The larger stack also maintains a heavy open-ended reasoning capability for ambiguous logic that the faster model lacks. Perfect automated tool scores do not automatically equate to superior general reasoning. The architect must choose the model based on the specific rigidity of the workflow. Single-node performance is dictated entirely by software-hardware alignment, not just raw parameter size. We have analyzed 2 validated states: force-fitting a massive model into memory constraints versus utilizing a smaller model executing native kernels. The 120 billion parameter stack is appropriate for tasks demanding deep, deliberate intuition and stable concurrency at the expense of speed. The 35 billion parameter stack is the choice for autonomous workflows requiring hyper-fast, precise tool execution and immediate responsiveness. Engineers should not accept manufacturer benchmark claims or default container settings as baseline reality without manually tuning the serving engine. Achieving true local AI sovereignty requires the architect to construct the engine around the specific workflow, moving beyond default deployments to engineer at the limits of the hardware.